Yeah, let me take this opportunity to thank the organizers. And yeah, I'll be talking on this projective knot theory, whatever the ideas are. And this is a joint work with my graduate student, Vishak Narayanan, who is working towards his PhD thesis. So it's all new ideas floating, and I would invite comments and suggestions. So whatever we have, I would like to just share. So uh, in low dimensional topology, like we are accustomed to studying three manifolds and knots, and theory of knots is related to theory of three manifolds and vice versa. And classical knot theory is the most common, which we have been studying for a long time. And they are studying knots in standard three sphere, S3. And we would like to, like a lot of people are studying knot theory in other three manifolds. So here I chose to study knots in RP3. The reason for the choice is for RP3, one can bring up even algebraic geometry flavor to it, because after all, knots are embeddings of S1 in RP3, and S1 is same as RP1. So one could think of embedding RP1 in RP3 and do everything in very algebraic way. So right now, I'm going to focus on more topological side, just comparing how classical knot theory ideas can be brought into developing knot theory for knots in RP3. And we would be seeing that the rich geometry of RP3 really brings a lot of good flavor to it. So formally, knots are like in RP3, knots are smooth embeddings of S1 in RP3, and the ambient isotopy is defined in a similar way that you can find orientation preserving diffeomorphisms from RP3 to RP3, taking K1 to K2. And the goal is the same, like classify knots on the basis of ambient isotopy. So the general principle is to define invariants, find effective invariants, which could help us classifying that. So in RP3, similar to classical knots, the theory of diagrams has been developed, and Julia Viro has been instrumental. She's developed the theory and moves, and even she has worked on defining Jones polynomial similar to Kaufman bracket, using Kaufman bracket from a diagram theory. So all that is being already known. So how the diagram works here is, in classical knot theory, you project it into a plane, and here you project it into a projective plane, RP2. So we all understand RP3, what it is like. You think of S3 and antipodal points identified. We can represent it by a ball model where the on the boundary, the identification is like the antipodal points are identified. So you take north and south pole and find there'll be an equatorial plane. So you could justify that every point in the ball has a unique circle coming from north pole to the south pole passing through it. And this circle will intersect the disk at a point. So that helps you defining a projection. So one could say that that gives you a projection onto a projective plane, and then you can develop the undercrossing, overcrossing information and make a diagram represent like this. And here clearly you can see that the points which are on the boundary, we always see the antipodal points are identified. So there are those identifications. And uh, in order to capture the isotopy at the diagrams level, we have Rydemeister's move. So there are those standard Rydemeister's moves which take care, which are anyway there. And there are some additional moves which take care about the identification part. So these are the, and we have similar Rydemeister's theorem, which I did not state here. So now where it differs, like in S3, this controversy is not there because S3 has S pi1 trivial. It's simply connected. Whereas when you go to RP3, your first homology group is non-trivial and it's Z2. It has two elements. So every knot, because it's S1, it's a one cycle. So it can either represent class 0 or class 1. And this is how a typical class 0 knot and class 1 knots would look like. And I would justify why this is class 0 and why this is class 1 in a bit. And another way of seeing that is you look at the two-sheeted covering. S3 to RP3, we all know there is a double cover. 2 points like a point and its antipode, they both get identified. And the first homology group of RP3 and pi1, they are isomorphic because it's abelian. And the antipode map from S3 to S3, that's going to generate the group of covering transformations. And if we look at the inverse image, if you have a knot in RP3, you take inverse image under pi, you get a link in S3. We call that a two-sheeted covering link. For a class 0 knot, the inverse image will be a link with two components, and those components are antipodes of each other. Whereas when you have a class 1 knot, the inverse image will be a knot. It would be connected, and that would be antipode of itself. And all that is very topological, and one could just derive those things. Now, let's look at a special class of knots inside RP3, which we would call them affine knots. So RP3, we can describe it as R3, in that you add a projective plane at infinity. So it's like another kind of compactification of R3. And every plane in R3 gets compactified as a projective plane. So when you take complement of any projective plane, that's going to be homeomorphic to R3. So we say any knot in RP3 is affine if it is disjoint from some projective plane. If it misses out any one projective plane, then that means it's affine. And affine knots, one could identify them as classical knots because affine means it's contained in R3, and from R3 to RP3, you have a natural embedding. So obviously all knots in R3, all classical knots are sitting in as affine knots, and vice versa. Even the equivalence, like if you look at them as knots in R3, and if they are ambient isotopic there, they would be ambient isotopic in as affine knots here and the other way around. So they're identical, and you could distinguish two affine knots using classical knot invariants. So the entire projective knot theory would be really for distinguishing an affine knot from a non-affine knot, or between any two non-affine knots. So we need to have invariants which help us discriminating whether given a knot, can we say it's an affine knot or a non-affine knot? Or if we know that both of them are non-affine, then is the invariant able to detect that? So as in classical knot theory, unknots are having an important role. So here we have two candidates which deserve to be unknots. So one is our standard unknot, usual unknot, which we call affine unknot. It's a planar circle which sits inside the interior. And another one is a projective line. So we know the antipodes are identified. So that's also a circle, and it's a projective unknot. So this is class 0 and this is class 1. So affine knots are all contractible. Therefore, they are homologically trivial. But all class 1 knots are non-affine, whereas non-affine knots may not be class 1. There are a lot of class 0 non-affine knots. So we have 3 distinct classes of knots to study in RP3: the affine ones, class 0 non-affine, and class 1. So non-affineness is something that we would be right now focusing on. The invariants that I am going to talk about help deciding whether a knot is non-affine or an affine knot. So the set of class 0 non-affine knots, that's a most mysterious class that we would come across. Now, the covering link for a class 0 knot is always a link with 2 component. And if the knot is affine, then the covering link has linking number 0, because there would be 2 disjoint copies and there won't be any linking. Therefore, if the covering link has non-zero linking number, that indicates that the knot is non-affine. So that's one of the ways. Now, like knot group. So pi1 of the complement in classical knot theory was one of the important invariants in the beginning. So similar to that, we could look at pi1 of complement of a knot in RP3. So Julia Viro and Oleg Viro, they have developed a parallel to this Wertinger presentation, which helps. So that is developed using checkerboard coloring of the diagram, very similar to the way it's done in classical knots. And one could write down the presentation for the knot group. And this is one important theorem, that knot is affine if and only if pi1 of the complement contains an element of order 2. So this is very algebraic proof. In due course, we will develop something which helps, which is more geometric and proves the same result, that knot is affine if and only if it's pi1 of the complement contains an element of order 2. So now I want to talk about diagrams in RP3. If you have knots in RP3, can we make it look like in some standard form? So some kind of structure theorem we would like to develop. So for that, this terminology of defining something called residual tangles, that's our own terminology. That so in suppose you have a collection of n mutually non-parallel lines in R3. Now the projective closure of this set is a link in RP3, because when you take projective closure, so the endpoints are on the boundary and they act like they are identified. So if we remove interior of a big enough ball in R3, so it's like this, you have a lot of lines and you inside R3, you choose a big ball and just remove the interior. So what remains is something like a tangle. So why we are looking at that? Because if you remove a ball from RP3, it separates RP3 into 2 parts. You have a interior, it's like a ball, and the complement is a mapping cylinder. So the intersection, the outside thing is like tangles, and we would like to name them, like how many are there. For instance, like this is, we call it T1, or this is T2, or you can have Tn in general. So nth residual tangle. So now suppose you have a separating sphere which separates it into a ball and a mapping cylinder. So the structure theorem that we prove says that if you have any knot, you take K to be any knot in RP3, you can always find a separating sphere such that the intersection of the knot with the mapping cylinder is a residual triangle. So what essentially we are trying to say is, in the ball model, we can put the entire crossing, all the knotting like an affine knot, and outside it's only bunch of arcs. So we call that sphere as a residual sphere, and the mod2 intersection number with any projective plane will be same as its homology class. So basically what we are trying to say is the number of times those tangles intersect. So the residual tangle that we get n, that n would be odd or even depending upon whether it's class 0, class 1 or class 0. Like for class 1, it's n will be odd, and for class 0, it's going to be even. So if we would like to see the proof, this diagram demonstrates the proof that you look at whatever the ball model. So inside that, if we can choose a big circle which contains all the crossings, then outside you will have some bunch of arcs. Now you can have several cases, like you can see that even though I drew a circle like this particular arc is not really going to the boundary. So what we can do is we can either enlarge it and make it intersect, or we can push it inside and draw a bigger ball and put this arc inside. Whereas if this situation occurs, we can enlarge it and bring it inside in such a way that these two will split into double, like there'll be, instead of just one arc, there are two tangles. So eventually we'll end up getting tangles outside this particular circle. And if you blow up this circle, it's like your residual sphere. So all knots in RP3 can be shown to have this kind of structure as a diagram. So now we have a notion which we call class changing surgery. So what basically we are trying to say is, if you have a diagram there, whether it's affine or whatever, if you add one more projective line to it, so basically you can take the structure of a residual tangle and add one more arc to it somehow, like T1, and that will, if initially if it was a class 0 knot, it will end up into a class 1 knot, and the other way around also. If it had odd number of TNs, like the tangles, and you add one more, that is going to become even. So from class 0 to class 1, or from class 1 to class 0, this operation can change the class of the knot. So now we want to develop a concept of companionship in like the way the notion of companions are there in companion knots in S3. So let us recall what we mean by a knot being companion to a knot in S3. So in S3, it's defined like that. You have a knot, you take tubular neighborhood of that knot. So that's a knotted solid torus. Now, suppose you have another knot K1, which lies in the same torus, but it is disjoint from K, and it should be geometrically essential, which means it should intersect with every meridional disk in V. Then in that case, we would say K is companion to K1. So we are not saying K1 companion to K. So the knot whose tubular neighborhood you are taking, that is companion to this knot, the other knot. And it's not symmetric. If K is companion to K1, it's not same as saying that K1 is companion to K2. K1 is companion to K. So one can show that unknot is companion of every knot. It's easy to prove. So now when we talk about companionship of knots in RP3, we want to develop the similar notion. So we take a solid torus, which is, suppose you have L, so a core circle of L, meaning like we are taking a tubular neighborhood of L. L lies in the core. Let L1 be another knot embedded in V, which is disjoint from L, such that L1 is an essential subset of V in the same way. So then, and also we say that this V is actually embedded in RP3. So then we would say L is companion to L1. So yeah, K is companion to K1, and the images, okay. So here in this diagram, I'm trying to show that this blank thing is, suppose you have some knot whose structure, like the outside this, you have a lot of tangles, and this torus is the one which is kind of like where your other knot lies. So here you can always find where everything happens in one torus and the other one is not containing any crossing. So you could construct, so what we actually end up showing is, in case of companionship in RP3, the projective unknot is companion to every knot, not the affine unknot. So we show using the topological structure of RP3. And so here, see, when you take a tubular neighborhood of any projective unknot, it produces a Higard splitting for RP3. And when you write the Higard diagram of RP3, it would be a 2,1 curve on the boundary torus of V. So using this notion, we define what we say untwisted Mobius strip. So when you take a framed solid torus and suppose you have M Mobius strip which is embedded in V, we say that M is an untwisted Mobius strip if the boundary of M is a 2-1 loop on the boundary of V. So how is this used? This concept is, you have, suppose you take a knot in RP3 and L is a projective line. You know, projective line, what is we call projective unknot, is companion to K. So choose one of projective lines which is companion to K. Then we'll say that K is projectively inessential if L has a tubular neighborhood which contains K and an untwisted Mobius strip which is disjoint from K. So now this concept helps us proving. So here we prove this theorem that a knot is projectively inessential if and only if it is affine. So an affine knot always contains a projectively like this kind of untwisted Mobius strip in a tubular neighborhood. And that helps us proving that it will, the pi1 of the complement contains an element of order 2. So this notion helps in proving the same theorem, that it's affine if and only if pi1 of the complement contains an element of order 2. So now we want to develop a concept similar to what we have in classical knot setup called genus. So genus there is very special, like genus helps us detecting unknots. So only unknots have genus 0, and you can have knots in classical knots, you can have knots of arbitrary any large genus. But here, the notion of ciphered surfaces which are used to define genus is not very adequate here, because you cannot really always find a surface which can bound a knot, because H1 is not really trivial here. So saying that we can always find a surface whose boundary is not our given knot, that will not work. So instead, we can have a closed surface which can contain a knot. So we don't worry about the boundary thing. We want to find a surface which is a closed surface which contains a knot. So whenever you have a closed surface in RP3, you take the double sheeted cover and take the inverse image. That would be a closed surface it will be a surface in S3, and it will always be orientable, the inverse image I'm talking about. And if sigma, the surface, is contained in affine region, then the inverse image is two disjoint copies of sigma. So now we'll say sigma is a surface containing a knot K. Suppose sigma is a surface containing a knot K in RP3. Then pi inverse sigma is a surface containing the covering link. So we want to give a definition that we'll call a closed surface containing a knot in RP3 to be a good surface for K if the inverse image is connected. It's a ciphered surface. So it need not be a ciphered surface. It won't be, in fact. So the inverse image is a closed surface containing the covering link. And if it is connected, then you call the surface to be a good surface. So we would want to ensure whether such a good surface can be always found. So suppose this is a affine trefoil. Now you just thicken the knotted, this tubular, whatever the thing that we are choosing, just thickening it and making it lie. This would serve as a good surface for affine thing. But for non-affine thing, it won't be so simple to establish. So we first prove that good surfaces exist for all links in RP3. And the way we choose, we can always choose them to be non-orientable actually. So to prove that good surfaces exist, let's take a knot in RP3, whether it's affine or non-affine, any arbitrary knot, and take a diagram of K on some projective plane. If K is an unknot, whether it's affine or a projective unknot, then there is a diagram with no crossing. The inverse image is a grade 2 sphere in S3. So we can just take that the unknot that bounds a disk, and the inverse image of P is so that projective plane serves as a good surface, because we take the unknot and make it lie on a projective plane. And I think there's some typo. So yeah, so the inverse image of P serves, which would be a grade 2 sphere in S3, and that itself serves as a good surface. But if K is knotted, then for each such crossing, we would attach a handle to P containing that crossing, and we will obtain a surface S containing K in this way. The inverse image S tilde will be a surface obtained by attaching handle on the grade 2 sphere, and the pi inverse P, which was a grade 2 sphere, similar handles will be attached there. And for each handle attached on P, there'll be double, like two handles on pi inverse P covering it. Therefore, S tilde is connected, and we can obtain otherwise also we know that this non-orientable surface S tilde is a two-sheeted cover for S, and that's going to be always connected because S is, if you choose S to be non-orientable. So the good surfaces obtained by this method are, yeah, above are construct all non-orientable because they're attached, they are obtained by attaching handles on projective planes. So they are non-orientable surfaces. So once you show that the good surfaces exist, so using them, we want to define that you take a link in RP3. Suppose sigma is a good surface for K, take pi inverse sigma, it's a closed orientable surface in S3 connected. So you can find its genus, the number of handles. So take the minimum genus of the inverse image surface varied over all the good surfaces. We would like to call it projective genus. And this would be an invariant. And the way it helps, first we ensure that the projective genus for both unknots, whether it's an affine unknot or a projective unknot, for both of them, the projective genus is 0. So the reason being, you can make them lie on a projective plane. The projective plane serves as a good surface, and its inverse image is going to be a great sphere, and its genus is 0. So both unknots have genus 0, but even the converse is true. Like if projective genus is 0, then such a knot has to be one of the unknots. The full screen, it hides. Yeah. So one could say, similar to classical knot theory, that something K is an unknot if and only if its projective genus is 0. But more important is, here the difference is the projective genus is very bounded for knots. For links, it can probably vary and give more values. So we are able to prove that the maximum value for any knot in RP3, the projective genus is bounded by 3, and all class 1 knots have projective genus 1. So these are like we could produce, for instance, if you take, so class 1 knots, when I say, I mean a non-trivial knot. I'm excluding class 1 unknot. So if you take class 1 a non-trivial knot, then its projective genus is 1, because you could find a torus as the inverse image whose genus is 1. And all affine knots have projective genus 2. The reason being, like when we can always find a torus for the affine thing, the tube, as a good surface for affine knot. And for that, when you go up, there will be a double of that. So the genus is 2, and all knots of projective genus 1 are non-affine. That is fine. Now what happens is, like, projective genus detects affineness, because if genus is say different from 2, then that knot is going to be non-affine, and all class 1 knots have genus 1. So what happens to those non-affine class 0 knots? That is where the whole mystery lies. So these are some pictures that I have drawn for showing the genus, like class 0 non-affine knot has genus 1, because you see here you can have even number of things. So one could always choose a good surface, a cylinder like this, and when you take the inverse image, it would be a torus, and these things will get identified. So these are some examples like this, but this picture, here we show that this particular surface that we are producing, its inverse image has genus 3. It's a class 0 knot because you have even number of intersections at the boundary. And but we still need to prove that genus is indeed 3, because you need to show that it cannot be less than 3. Like you cannot find any other surface whose inverse image can have genus smaller. So that still is not shown. And this is a picture for genus 1 class 1 knot. It's a projective line. So actually we should here, this is not we shouldn't say it's an unknot, but this is just a picture that if you take a cylinder like this, the inverse image is going to have genus 1. But we know that if it is a line, it's a projective unknot, then you can have actually another good surface whose inverse image has genus 0. So that's not really minimal. So projective genus for class 0 non-affine knots are the one where all kind of segregation happens. Like you can have genus 1 non-affine, genus like class 0 non-affine. They can have examples with genus 2. And so they come in 3 different classes. And we have examples of each class, but complete classification would be more interesting to produce that precisely these are all genus 1 non-affine, class 0, and class 2, genus 2 and genus 3. So this is still work in progress. So I would like to, maybe I finished quite early. So maybe this is all.
Thank you, ma'am. Any questions?
It would be interesting to know about cobordism of knots in RP3.
Right. I have been thinking about it. Only last night I was thinking that to develop cobordism theory, and then that would, so even like all these polynomial invariants, also we are on to it, like develop a Jones-Witten theory to define, because the diagrammatic way of defining polynomials, this Jones polynomial is there, but in classical knots, the Jones-Witten theory and this, because of the skein relation, one can prove that if you come up with something else, you could say that it satisfies the same relation. But here we do not have any skein relation yet known. So yeah, thank you.
Well, you do have skein relations for a bracket in RP2, like Julia Vero did.
Right. So that could serve, that could probably help us if we come up with something else showing whether it is same as that. But
there's also the skein modules. People must know about the skein modules for RP3. Yeah.
Right. That I think is known, that I've seen. But yeah.
Is it possible to define virtual knots also in RP3?
Virtual knots, actually the whole idea of virtual knots is like replacing S3, like the 3 manifold is a thickened surface. So surface cross interval, that's the theory of virtual knots. So virtual knots are already knots in some 3 manifolds. So I don't think that knots in RP3 can have another virtual component.
Well, we can consider knots in thickened non-orientable surfaces.
I see. Yeah, thickened non-orientable. That would give rise to a virtual.
And that's a virtual knots with an unorientable version of virtual knots.
I see. Yeah. Good. Yeah. Yeah, thanks. I didn't think about it like thickened non-orientable surface. Yeah, good.
Any other questions?
I have a question. Any node on the projective space can be lifted to the link in the S3, right?
Right.
Is it true that if nodes in RP3 are different, then lifts are also different?
So the other way around, if they are same, then the lifts are same.
It's evident, of course. But if, or maybe another version of this question,
if the lifts are equivalent, can you say the knots are equivalent?
yes.
I think that won't be true. That won't be true because so the thing is like you can have a version of something.
But examples are known.
Yeah,
Yes.
that won't, you can produce examples where as a classical thing. So here it's link. So you can always have two component links with some kind of linking number different, and there when you come down they can, here you might have something equivalent, but when they go in RP3 they might not be same. Yeah, I think the other way around, it's not true. It's just that I'm not able to think an example. Only one way, like if your knots are equivalent in RP3, then the lifts will be equivalent in S3. But one could produce examples where the lifts are equivalent, but this here they are not.
Okay, you believe that there are examples, right?
Yeah. I think even I had seen examples. It's not coming to me. Yeah.
Really? Interesting. Thank you. Yes.
Any more questions? If not, let's thank the speaker. And next talk will be after 15